Hello, RubyC. Hope you're still awake, just before lunch. So I'm going to talk about parallelism and thread safety in Ruby, and I'm working on TruffleRuby. I will explain in a second what it is. First, I have to show you this slide to say that TruffleRuby is still a research project, essentially, and not yet a product. So I'm Benoit. I'm working in Switzerland at Oracle Labs. I've been doing a lot of research. I did a PhD basically on concurrency. And I work on this TruffleRuby project. I did that for almost 5 years now. I'm also the maintainer of Ruby specs, which is a set of specs for the Ruby language. And I also contribute to the standard implementation, CRuby or MRI. Sorry. So today I want to talk about two things. I want to talk about performance, because it's kind of one of the main goals of TruffleRuby. And then I want to talk about my research. So TruffleRuby, if you don't know it yet, is a high-performance implementation of the Ruby language, and it's done by Oracle Labs. So its aim is really to be much faster than MRI on any kind of workload. And to do so, it uses a just-in-time compiler, which is called Graal. It targets full compatibility with CRuby, even C extensions. So the ideal would be like you can use your app, you can just run it on TruffleRuby, and it should just work. We're not there yet, but we're making good progress. It's just on GitHub, it's open source if you want to have a look. So there are two ways to run TruffleRuby. The first one is to run on a Java virtual machine. The main advantage there is you can interoperate with Java, so you can reuse Java libraries, for instance. And this will provide great peak performance. So peak performance would be after the application warms up, what performance do you get? And then the second way, which is actually the default, is on Substrate VM. So in that mode, we compile both TruffleRuby and the Graal just-in-time compiler ahead of time to a native executable. So this looks a bit like MRI. The end product is kind of an executable with everything inside. And it's not longer really look like a Java virtual machine. So what we get in that mode is we get much faster startup. For instance, to print hello world takes about 18 milliseconds. This way, like on a typical JVM, would take at least half a second. And this is actually even faster than MRI startup, which is quite incredible. We also get a bit faster warm-up, so the time to get to peak performance, because both the TruffleRuby interpreter and the JIT are already pre-compiled, so themselves, they don't need to be just time compiled. Finally, we also get a bit lower footprint, simply because we don't have to manage all these kind of classes at runtime and so on. That's a bit more complicated. And in the end, we still get a great peak performance. So you might know about the Ruby 3x3 project, which we already mentioned once today. So the goal is to make CRuby 3.0 to be 3 times faster, and here's the catch, than CRuby 2.0, which is very old now. And the way that CRuby intends to do this, mostly, I think, is with a just-in-time compiler, which is called MJIT, simply for MRI JIT. And so the question is, can Ruby be actually faster than 3 times CRuby 2.0? And to answer this question, I want to make a small demonstration. We'll run what is called OptCarrot. It's a CPU benchmark intended to measure Ruby 3 times 3. At least part of it. And it's actually an emulator for the Nest system written entirely in Ruby and was created by one of the CRuby committer, Yusuke Endo, also known as Mame. Okay, so first I will run on Ruby 2.0 because this is the baseline. Yes. Exactly. And so here we have the game. And we see it runs at around a bit less than 30 frames per second. And this is not so good because the normal Nest system runs at 60 frames per second. So if we play a bit, you will see it's quite slow. Like you can already see in the logging time. So the aim of the game here is to connect all the computers together. So you see here, it will finally say that I passed the level. So it's not exactly reactive. So we can try on the latest and brightest Ruby. And there it's already a bit faster. So here we are like 40 frames per second. And we can also try MJIT. by passing a JIT flag like this. And there we get around 50, yeah, even 60 frames per second here. It reaches 60. So that's quite nice. It's still like not 3 times faster than 2.0, but it's getting closer. But then what happens if we try with TruffleRuby? So yeah, run it in the JVM mode. I presented 2 modes earlier. So the first thing is going to be quite slow, because it needs to learn what the program is doing. And then it needs to compile what matters and start to optimize that. So if we wait a little bit, as it understands exactly what this whole game is doing, then it gets interesting. So we get around 200 frames per second. Yes, now we are here. And that's quite nice compared to like almost 7 times faster than 2.0. And we can start playing. Of course, we surprised it, right? Didn't expect that, like, oh, wait, this is another part of the program I had no idea how to execute. But it will learn. And now I can play, and it's a little bit more enjoyable because I can move around in decent time. Now, I have another problem is that the time counter on top is based on frames, so it means it's actually run faster than real time. Yeah, it needs some time to get stable, I think. Okay, here we go. And actually, I did it wrong. Like every good old game, it's meant to trick you. Yes. Ooh. Okay. Okay, so what we saw here is like here we have a warm-up graph. So you see that TruffleRuby initially was quite slow. And the reason is the interpreter in TruffleRuby doesn't just execute the program. It also sees exactly what you're doing to be able to learn from it and to be able to optimize it. So for instance, every branch of a heap that you take, it will know if you took both branches or only one of them. And then if it's only one of them, it will only compile that branch and the rest just assume it's not taken. And so what we can see here is TruffleRuby, once it has warm-up, is like quite a different level of Ruby performance that we are used to. Here it's like around 200 frames per second instead of something like 30 to 60. So that's quite nice. And we see this not only on OptCarrot, but also, for instance, here's a set of classic CPU-intensive benchmark. We see that TruffleRuby is also much faster. Like here, it's around like 10 times faster on many of the benchmarks compared to CRuby 2.3. Here is a bit old. Of course, it doesn't work for every program. So, for instance, PyDigit there it's not much faster because it's just big integer computation. So that's the same on every platform, basically. MJIT itself has some micro-benchmarks that were like designed to really assess the performance of the JIT and like if the optimization work as they intended. And so the baseline here is CRuby 2.0, and this is a variant of MJIT. And that variant is about 4 times faster than CRuby 2.0 on this micro-benchmark. JRuby is about 2.5 times faster, but TruffleRuby is like here 30 times faster. So it's like, again, okay, on CPU-intensive benchmark, we're doing great. The other areas, so for instance, we work on ERB templates. If you run a small ERB templates, we see it can be like kind of 10 times faster than MRI. And the reason of this is a different representation for strings. So normally, when you append to string in Ruby, you would have to copy, relocate a buffer, and so on, which is quite expensive. In our case, we use robes, which is a technique also used in code editors. And that means basically you just create an object that says this is the virtual concatenation of these 2 strings. And that's much faster. There was a talk by Kevin Menard at RubyCAG a couple of years ago. And then there are other things, but let's focus on the talk. Of course, the main question is, do you run Rails yet? And Well, it's a difficult question to answer. So yes, we run some part of Rails, and for instance, we have a small blog app that we actually test in CI. And this one works now both on Rails 5.2 and also Rails 6. And it also uses different database adapter like Postgres, MySQL, or SQLite3. We're working currently on better compatibility with more Rails apps, and then notably Discourse is well known, and other larger Rails app. And we have some part working already, but we kind of need to fix like the underlying bug behind it, so it just works out of the box. That's the aim. Of course, like the hard reality is like most Rails apps have a lot of dependency and a lot of C extension, and so there's always one thing that kind of you need to fix. But for C extension, we got a new approach recently in the previous release, where we do something which is more similar to MRI. So the conclusion of that is basically many more C extensions just work out of the box. We don't need to do anything, just gem install it and that's it. So for instance, here we support some of the most well-known C extensions like OpenSelp, SIG, Zlib, Puma, SQL3 already mentioned, and so on. So in this talk, I want to explain you a bit how do we reach this performance, to give you some insight into that. And this is due to mainly two factors, which is partial evaluation, which I will explain a bit, and the Graal just-in-time compiler. And on the implementation side for TruffleRuby, it's a mix of Java and Ruby. So some core things like integer plus are implemented in Java, and then the rest of the core library would be written in Ruby, much like in Rubinius. So the first thing a Ruby interpreter does when it wants to run your code is to parse it. And then here we have a very simple example. We have a foo method. And it just takes an array and triple every element, right? And the first thing I do is parse two abstract syntax tree, but actually not one abstract syntax tree. It's one abstract syntax tree per method or per block, actually. So we have the foo method. We see we can have a small tree here on the left, which represents it. And so what the foo method does, it calls a method map, and the receiver is an array literal, and the arguments, well, there are no arguments, it's just the block. And then we can imagine the block is a different abstract syntax tree here, and what it does is multiply the argument by 3. And then map, we can also imagine it could be implemented in Ruby, for instance. It's also its own tree. Then it will read some element of the array, build a new array, and call the block for every element. So what we do in TruffleRuby is instead of building a normal abstract syntax tree, we build what we call a truffle abstract syntax tree. And there is not much difference. The only difference is that every node is actually an object, a Java object in our case, and it has an execute method. So every node knows how to execute itself or to run that part of the program. So here, for instance, we have a multiplication node, and it just says, oh, execute the left child, the right child, and then multiply them together. Now we can get to partial evaluation. The idea with this process of partial evaluation is we will take this truffle AST of a Ruby method, for instance, the AST of foo, and what we will get is a compiler graph which represents how to execute this Ruby method. And then with this compiler graph, we'll actually give it to the just-in-time compiler that will produce native code. And I will show you the process interactively. So here we have our little tree for the foo method. And so each node here, we have the definition of the execute method next to it. So to execute foo, what we do to execute a method is we just execute every statement or expression in it. In this case, there's just one, so we just execute that one. So this one, we imagine, okay, there's a child node, a field here, and we say, okay, go to execute that call. The interesting bit here is we know we are compiling foo and nothing else. So when we refer to the child here, which is the field of that object, and we know it cannot change, it means we can inline. We don't read from this field. We know everything when we are doing partial evaluation. Sorry. And then we get to this call node. And then again, when we execute it, well, we have some logic to call a Ruby method. But before doing any of that, we have to execute the receiver and the arguments. And the receiver itself is this array literal with 1 and 2. And so again, here we'll then inline how to execute the receiver. And the receiver happens to be this array literal, which just create a new Ruby array instance with a value inside it, and each value is an integer literal node. So what we get when you do all this process of partial evaluation is you get something like here below, We have, okay, the logic to call a method. We already know we call map and nothing else. That's part. It was part of the syntax of the original program, and we're sure we can only call that. We know we'll call it with the receiver is a Ruby array, and we know the elements, and then we call it with some block. So if we do this not only for the foo method, but also for map and block, we have similar things. So map here will just create a new array, call the block for each, and block will just multiply by 3. Now the interesting bit is like most language implementation will also have inline caches. So it means like whenever I do a call to a method or to a block, we'll remember what we call. So the next time we do, we don't have to look through all the classes hierarchy to find where the method is. We can just say, oh, if it's the same class and nothing was redefined, then we can just call the same method again. And so we have this red arrow here, which is like, oh, this call actually it knows it calls map, and the call block in the map knows it calls this block. So if we rearrange this a bit, it's very easy to do this inlining in the OST. We just like say, oh, we present just one big tree, compile it together. And what we get, so when we took these 3 Java methods before and we put them in one, we get something like this. Now, what we can do is the compiler can jump in on this and start to optimize it. So the first thing it notices is that this array on top, here actually this instance never escape. Like it doesn't escape the method, it will not be used after. So what we can do is we can say, well, we don't need this instance, we don't need to allocate it. We can just basically deal with whenever it's accessed. So here we would access the size, and here we have read elements from it. We can just, the size always 2, we know it. And to read an element, we can just read from the underlying storage, which is here int array. Then the second step here we can do is like when this check here, that the element of the array is an integer, because then we need to know how to multiply numbers, right? So if it's an integer, we do it one way. If it's another way. Here we are just proven, right? Because we read from an int array, so this has got to be an integer, so we can just remove the other code. So the interesting bit is that here the compiler noticed there's this loop, and it only has 2 iterations, always 2 iterations, and there's not a lot of code inside it, so we could just duplicate the code for every iteration, then we just don't need to have a loop around it, which simplifies things quite a bit. And then finally, while reading from this array storage, we just allocate it, is trivial, right? The compiler can figure out that, okay, array storage 0 is just 1, and the other one 2, so it just does this. And then, well, the compiler hopefully knows how to multiply, and this one, what it does, this multiply exact is check for overflow, but 2 times 3 doesn't overflow, we know it's just 6. Can we pass that by that? We arrange the code, and we got this. So this is quite nice, like compared to original code that would take the full slide, now it's quite simple. And so what we did is with partialization and the JIT compiler is compile this method to something very simple. Basically, like here, this method of compilation understood what the Ruby code wanted to do, understood what map does, to a point that it can just tell you the final result. And so, yeah, we could see it as Ruby code too, then it's very simple. And can imagine now what we actually limit is assembly for it, but it's extremely simple. It's like allocate an array, write 3 into 6, write 6 into it, and that's it. So now we can compare with MJIT. So the JIT for MRI, also called, the M also stands for MetaJIT. And as I said before, the first thing an interpreter does is pass it to an AST. But then after, what they do is they transform this to bytecode, which is basically a different representation for it. And then when I make like a typical JIT, when a method is called many times, you call the JIT and say like, hey, it would be good to optimize this method if you can. And the way they do it is like they take this bytecode and they generate C code from it. And from the C code, they will then call a native compiler like GCC or Clang to create a share library with this C code, with the compiled C code, then load the share library and then call this function. So what happened is then this Ruby code with MJIT is kind of compiled to this C code, which is here a bit simplified for readability. Basically, you see, yes, it does a new Ruby array, and then it will do this RB fun call. And then you can imagine the block itself is also compiled to C code. And basically say like, oh, if both are integer, then we'll multiply them. It's quite easy. If both are float, I do it another way. Otherwise, I have to optimize, which is like, okay, then I need more complicated logic, and I will need to recompile this. And what comes in after this is that the native compiler, so GCC or Clang, can try to optimize it. And what can happen here, it will say like, well, there was this like, is 3 an integer? And it's like, well, yes, 3 is an integer, so it's not going to be a float, so I can remove this branch. But that's about it, basically. The compiler cannot go further. And the reason for this is that the implementation of map here, which is actually called arbitrary map, is part of the Ruby binary. So just the compiler has no idea what it is, how to deal with it, or how to inline it, or anything like that. So for this particular example, MJIT basically wouldn't give anything because it doesn't have enough information. So I want to do an intermediate summary here, which is like, I think the performance of the Ruby language can be much better, can be improved quite significantly. And TruffleRuby is an example of this, at least on some of the benchmarks. So what I'm saying is basically, I don't think there's a need to rewrite your application in another language for speed. Like for instance, Ruby can be basically as fast as the state-of-the-art JavaScript engines. And one of the key parts for this is, well, you need a JIT compiler and it needs access to the core library. It needs to understand what array map does. It needs to understand what the enumerable method do, and so on. And it also needs to understand what the Ruby construct do. So for instance, the MRI, it could be quite a challenge for MJIT to just understand the concept of allocation. Because when we allocate a Ruby object in MRI, what we would do is just bump a pointer and write to the heap. But doesn't understand that, for instance, it could remove this if the object is never used later on. So that was the first part. Now let's talk a bit about parallelism. So when I started my PhD, I saw like one of the problems I wanted to work on is like, and one thing I noticed is like dynamic language in general, be it Ruby, JavaScript, Python, or anything else, have really poor support for parallelism. And this is actually not due to the language. The language are kind of nothing wrong with them, but due to the implementation, which usually restrict what you can do quite a lot. So for instance, here I made 3 categories, and the first one is the global lock. So CRuby or CPython, the standard implementation of Ruby and Python, they just use a global lock for the whole VM, which means they can never execute Ruby code or Python code in parallel in a single process. It means the only way to scale then is to use multiple processes, which makes communication harder and, of course, tends to waste resources and memory. Now, there are implementations that work around this that don't have a global lock in Ruby, and for instance, we have JRuby and Rubinius. But one problem here, we'll see, I'll explain later in detail, is I will call them unsafe, because there's a basic method, like for instance, appending to an array. The documentation would say, well, add an element at the end of the array. But on JRuby and Rubinius, it becomes my add an element on an array, or my throw an exception, which is not exactly what to expect. And then finally, there is the third category, which is the share nothing or share little, which is basically, well, they work around the problem. They say, oh, we don't have shared memory, so we don't have to solve this problem. But then it means you have to write your program very differently. It means you cannot have mutable state, or you cannot at least pass it around conveniently. So in this, we have, for instance, JavaScript, which doesn't share memory at all, Erlang, where there's simply no mutable data structures, or guilds for Ruby 3, which I will explain a bit more. So guild in general, I think one of the main advantages is that it has a stronger memory model than the current Ruby 2. It means that we don't have low-level data races, and I will show example later, because of how it's structured. But then the big disadvantage is when you have an object or a collection and you want to pass it between multiple guilds, well, you either have to copy it or you have to transfer ownership. And actually, transfer ownership is just a lightweight copy, so it's not much better. So the question for me is like, well, this has some cost to copy or to transfer ownership, and it's unclear how this is going to scale. Basically, also, like the only way to have mutable state in such a system is to put it within one guild, and then everyone has to access that guild. So, like, how do we deal with that? How do we scale that if we need more CPU power for it? I think like Erlang and Node.js, for instance, work very well for your workload, Because, well, I.O. you don't have this problem. You don't need so much CPU power. But what if you are more CPU-based? Then I don't know. It gets tricky. Of course, like existing Ruby libraries use Ruby thread, and they would need some serious rewriting if they want to use guilds, because it's a completely different programming model. It's more like actor libraries. But in the end, I think they are complementary. We can have both shared memory parallelism and something like guilds. And some of them work very well for some problems and some for others. It's just, there's not silver bullet for concurrency in general. So I was calling JRuby and Rubinus unsafe, and I want to clarify this. So here we have a simple example. So we have an array, and then we have 100 threads that will try to append at the same time on the array. And they will each append 1,000 elements, so we should end up with 100,000 elements. Then we wait for each thread to finish, and we print the size of the array. And sure enough, if we run this on MRI, then we will get the expected result. But if you run this on JRuby, you get either a random number, which means some of the appendages they were not there, like you did something, but actually nothing happened. Or you get an exception, depending on your luck. And then this is not only JRuby, Rubinus would get the same thing, basically, either a random number or a different exception. And something I wanted to work on was like, well, we want parallelism, but we also don't want to break things like basic things like arrays in the core library. So a workaround that JRuby or Rubinus people will tell you is say, well, you can use a mutex or you can use concurrent array. And this, well, it works around the problem, but it has other problems, basically. First, it's very easy to forget to use one of these, and if you don't, you get one of these exceptional random number, which is not exactly nice. And then if the synchronization is actually not necessary, like if you add too much of it, then it adds quite significant overhead. And both of these solutions actually prevent parallel access to the array or the hash, which, like in parallel programming, would be weird, because like if I have two threads, they work on different parts of the same array, they should be able to run in parallel. There's no reason to make them wait one another. But I think the biggest point against it is like from a user point of view, array and hash are thread safe in MRI, and so there just should be for the implementation, otherwise some form of incompatibility. Well, the reason they do this, of course, is because it's not so easy to solve. Like, how can we make collection thread safe and at the same time not have a lot of overhead, like notably on single thread performance? Because if you just had a lock, for instance, across every collection operation, your performance could be 10 times slower for some array operation, for instance. And one thing I want more is parallel access, I just mentioned on array and hash. And this is actually not only a collection, it's also with objects. Because objects in dynamic language are basically like hash tables to some degree. You can add or remove field at any time, which means the representation is quite complicated, which means you need synchronization to do it correctly. And if you don't have any synchronization, you can get things wrong. So for instance, this can happen on Rubinus. So you would create an object, and then you have two threads. And the first one would set the field A to 1 and then to 2. And the second thread would set the field B to string B. Now the thing is, we have some storage to store the value for this object. At some point, we might have to grow it. So here, okay, we could just write 1 in the values, but here we have to expand it because we didn't have enough space anymore. And by expanding and copying here, we actually take a snapshot of the value, and it means we undo this. So the end result would be 1b, which is incorrect, like this assignment 2 was just lost. So we also need synchronization for objects. And one of my ideas here, how to solve this without having a lot of overhead, would be to separate objects into two categories. So we have what I call local objects, which are only reachable by one thread. So if only one thread has a reference to this object, then it cannot be accessed concurrently. Only this one thread can access it. But then for other threads, I would call them shared. Other objects, I would call them shared, and then I would use synchronization. And the idea there is like most objects in Ruby, they are not shared between multiple threads. So actually, the one we need to synchronize is a small proportion of all objects in the system. So let's have a look here how it would work. So we have a couple threads which refer to a few objects. What happens if thread 2 starts to reference this queue? Then we would mark the queue as shared, so a blue here on this diagram. But not only the queue, but everything reachable from it. Because of course now thread 2 can access the message, the hash, and the key and the value. And to maintain this set of local and shared objects, what we need at runtime is a write barrier. So whenever we write to one of these shared objects or shared collection, whatever we write into it, we have to mark it as shared transitively. So here we write to a field of a shared object, we would have to share the hash, the key, and the value. And the same for the collection, whatever we put into it, we would need to mark it as shared and to synchronize on them. And with this approach, well, the first thing is like the single-threaded performance doesn't change. Because for single-threaded benchmark, basically all objects are local. The only exception is some global constants, global variable, and so on, but they are not used typically in the benchmark. And so what we see from unsafe to safe, so this is TruffleRuby without the fix, and this is with this local and shared distinction and proper synchronization, we see there's no performance difference. On the other hand, if we would synchronize like on every object write, which is, for instance, similar to what JRuby does, we could see like there might be at least 2 times slower benchmarks here, here, and here. And then we can have the same for collection. If we synchronize collection, we run similar set of benchmark. We see, well, there's no overhead for single-threaded benchmark because they are all local, basically. So let's take a look a bit at arrays more in details. So arrays in most dynamic language VMs actually have a complex representation here, which are called storage strategies. So basically, how we represent the array changes based on what it contains. So let's take the example. For instance, if we create an empty array, this uses an empty strategy. It doesn't allocate anything. But then if we append an element to it, then it switches to this int array strategy. And the advantage of this, it means like for each element, if all elements are integer, it uses only 4 bytes per element, which is quite compact. It can just access the value directly. There's no pointer tagging or anything like that. But then if we put a string into it or some kind of object, then we have to migrate to the most generic strategy, which is object array. This is less efficient, of course, if we end up with integer in it because we have indirection and so on. Now, when I work on this thread-safe array for TruffleRuby, I wanted to, of course, support all operations. They should all be transparent. The user shouldn't have to care about it. And I wanted to preserve this storage strategy because they give quite a lot of efficiency. And then finally, I also want to enable parallel reads and writes to different parts of the array because some parallel workloads just rely on this. So what I did is make the diagram more complex, or another way, add 2 more strategies. So here we have this set of concurrent strategy, which actually there are only 2. There's this shared fixed storage and shared dynamic storage. The idea for this shared fixed storage is like, well, some of the array, they never change their size. They're kind of fixed size arrays. And for this one, we can optimize much better than for arrays on which you can do all kind of operation, like delete an element in the middle and so on. So for this one, actually, we don't need, for shared fixed storage, we don't need much synchronization. But for shared dynamic storage, then we just use a log because there's no way to support all the methods of the Ruby array without proper synchronization there. And if we look at the performance of just reading from an array and writing to an array, and we do this from 1 to 44 threads, we look like, well, the first here, so the local and shared fixed storage, the 2 blues, they scale perfectly, and they reach around 30 billion array access per second on 44 cores, which I think is quite fast. And yeah, the reason that shared fixed storage is so efficient because it assumes that, okay, the size of the array doesn't change, so I don't need synchronization. I only need synchronization actually when this doesn't hold anymore. But then all the other ones, they're all variants of this shared dynamic storage with different kind of logs. And we see they're much slower, at least 3 times slower, because every time you desynchronize, it's a lot slower. And here we have different logs. So one of them is reentrant log. It's a bit like the global log. Like it's just a simple mutex. And well, this doesn't scale at all, right? It's just actually slower on 44 threads than it was on 1. So that doesn't help, obviously. And then we have something like a stamp log, which is like a read-write log. So it means the read can execute in parallel, but writes cannot. So it scales well for... Sorry. It scales well for read, but it doesn't scale at all for write here. So we use something a bit more fancy, which we call the layout log, which has 3 operations. It has read, writes, and layout change. And layout change is like, well, I have to completely rewrite my data structure because someone deleted an element in the middle or change completely the type of object stored in it. And that one then will be exclusive, but read and writes, both read and writes can execute in parallel. And so it also scales that way. I've run this on larger benchmark, which is here the NASA parallel benchmark. That were a very old benchmark, actually, written in Fortran originally, and then transited to Java, and then to Ruby. What we can see here about scalability, so how much times faster on n thread is it than on one thread, is that it scales basically just as good as Java and Fortran. And this is with the synchronization, well, like the dark blue is with the proper synchronization, and the light blue is without. And we see, well, basically they both scale very similarly. So in conclusion, what I already said, I think the performance of Ruby can be much better than it is today. And TruffleRuby is trying to show this and to expand the use case where we show great performance like this. We can have parallelism and thread safety in Ruby, and there's no need for global lock intrinsically. And we can still have no single-threaded overhead altogether with that. So I hope that with this, basically, we start writing more parallel Ruby code. We expand a bit what we can apply Ruby to. We can start to do like compute-intensive stuff, matrix stuff. There's no reason this can also run in Ruby quite well. And we still get the important thread safety guarantee that we are used to with the GIL, but we can also scale to many curves. And yes, if you want to try TruffleRuby, you can use your favorite Ruby manager or installer. Just integrate it. If you have any feedback, whether it's a bug or whether it works well, please tell us about it. We are very happy to hear about that. And finally, TruffleRuby is part of a bigger project, which is called Graal VM. And the latest release is 19.2. And there's both an open source edition, community edition, and an enterprise edition. The reason for the enterprise edition is, of course, we need to fund all the big team that's working behind it. And we expect like bigger enterprise to want support and so on. And so that's why it's there. Graal VM, in addition to TruffleRuby, also offer many other languages. So we have a JavaScript implementation, we have a full Node.js implementation, we have a R implementation, a Python implementation, and also a LLVM bitcode implementation, which means you can execute C, C++, and Rust, and so on. And all of this in a single VM. So in the same process, you could execute all these languages. They could call each other, and you can even inline and optimize across language boundaries. So this is quite unique into what makes Graal VM. It also has a tool which is quite well known now, which is called native image. And it's very related to Substrate VM I mentioned before. The idea is you can take a Java application, you can compile it ahead of time to just a native binary. And the main advantage there is, of course, you have very fast startup. And finally, we also have some tooling which works across all languages. Also, we have a mix of languages, which is, for instance, we have just CPU profilers, memory profiler, debugger, and more. And that's it. Thank you for listening, and I'll be able to take some questions.